Yeah, so thank you, Kevin. Thank you, everybody, for attending, coming to this talk. So today I'm going to be talking in general about quantum simulations, the immediate and the prospective applications for different industries. So the agenda for today is, of course, I'll introduce myself and what actually really motivated me to start BQP or BosonQ side, and how there is a need to kind of transition from traditional computing to quantum computing, and then look at what can be done using quantum, or for the need to change from traditional to quantum. What type of applications are we specifically needing it for? And then lastly, I will talk a bit about what we do at Boson QSI, what we are kind of developing, our trademark software BQ5, which is a quantum-based simulation software, and I'll go a little bit more in depth then. So, okay. So yeah, a little bit about myself. As Kevin and I was just talking, I was in a PhD program at University of Minnesota, doing my PhD in computational fluid dynamics, or CFD, in the hypersonics application. So specifically, I was doing on hypersonic vehicles, the essentially air breathing engines specifically, and the interactions, the fluid structure interaction that's there. So I come purely from the applicational industry. So quantum as a whole was, when I got introduced to quantum, which was not too far back, I came to realize the quantum and the need for quantum from needing it from application, because doing these types of CFD based applications or use cases, it would take tremendous amount of time. And personally, I've seen it myself, as well as my whole research group, which is one of the leading groups in hypersonic research. And there have been times where the actual a single use case or a single simulation took over a month to perform. And we're talking, trying to match the simulation with what the exact results are. And so that's the ultimate goal of any simulation engineer, is to eradicate the whole need of experiments. And that's what we want to get to. And so that is what kind of motivated me, and along with my founder, that's where we kind of came along and realized that we cannot necessarily do it with the traditional power of computing that we have. And there are many reasons for it. And looking from purely from application or industrial point of view, there is a big disagreement, or let me just say discontinuity between the industry and the academia. So in academia, we have the leisure of not doing what we want to do, but we can spend resources in computing, as well as we have time, especially for PhDs, we have some time to really spend time and not worry too much about how long these simulations and such takes. However, for the industry, the time to market is very, very crucial, where they are willing to give up accuracy in hope to make up for time. And so that is, from a very applicational point of view, that's not a great thing to hear, because you see over and over again different recalls, from safety to malfunctioning and things along those lines. They are coming over and over and over again, and that's purely due to not having enough time for engineers to fully, thoroughly test not each and individual component, but even as a whole, they're not even able to test it that rigorously to ensure that, okay, this finalized product will not have any form of defect or recalls. And the second point of why we need why, from the industry point of view, what they want to get towards is this whole aspect of digital twin. Some of you might have heard this concept, but it is essentially the industries want to digitalize everything. So they have a physical world where all the manufacturing, physical testing, and all such is going on. But likewise, you want to have everything on the digital sense as well, and that's where the new technologies of AI, blockchain, the AR, VR kind of technologies are really coming in and playing a role, is even in the industry level, where they want to create this meta or digital world where simulation, everything is performing on simulations, and then those simulations needing to predict what actual experiments can, or what physical world can do. And if you can predict that, you can kind of do predictive response rather than reactive response, which is what we see often and often again in various different industries. And so the whole topic is then, okay, now we need more computing power. However, from traditional computing, we are nearing the end of Moore's law, where, which is essentially in every so often, about, I think about 10 months or so, about 12 or 18 months, the size of the chips, the computing chips, reduces in half, which in then basically for the same size of the chip, your computing power doubles. Now we're at such a small chip size that this doubling power can only go for maybe a few more years before we go into quantum realm automatically, and where quantum effects really start playing an effect. So you cannot just infinitely divide it by half the size of the chips indefinitely. You cannot do that. So automatically, you have to go towards quantum. Like logically, you have to go towards quantum. And there's also another aspect to it, the Dennard scaling, which is essentially looking at how the power density in a specific chip is. And so as the number of transistors increase, in a single computing chip, the power density also increases, and that can cause a lot of problems due to overheating. Well, that's mainly it, to be honest, overheating. And we're talking about producing so much heating that the efficiency of the transistors themselves are decreasing, as well as the overall power output or power input that is required is tremendously increasing. And so, yet, these are all physical restrictions that we have from computing technology. But the industry, the applicational industry, they are always going to be asking for more performance and higher accuracy. That is always going to be there, where industry will never have enough performance and accuracy, and they will always have the need for higher computing power. And so automatically we have it's logical that we have to go towards quantum. And so there are a couple of aspects of quantum where we cannot necessarily readily use full-on NISQ or noisy intermediate scale quantum devices. We cannot necessarily use it right at the moment due to several reasons, but most of it is because they're quite noisy, as the NISQ short form kind of entails. So there are other approaches that we can currently use, which can provide more an answer compared to our traditional computing. And so this leads to quantum inspired approaches. And so you have your quantum inspired approaches, then the NISQ era, like I was saying, these are the annealing and the gate based, that there are two different architecture in the NISQ era. And then you have the utility of the NISQ era quantum computer, where the two main component that we really care about is the qubit count and the quality of the qubits and the gates. Specifically, when we say quality, it's more about the decoherence time and the gate depth itself, as well as the coupled qubits for specific types of, when you're looking for specific types of applications. And so looking in the near term, what really is the best, or the best answer for utilizing quantum technology is to utilize quantum principles in your simulations. So this first example of mimicking turbulence structure, it's actually researchers are trying to use quantum phenomena to see to replicate the randomness of the nature of turbulence. And to give you a little bit of background on what turbulence is, it's a very erratic, unpredictable nature of usually in fluid flows, but it is also in other areas as well. But there is structure in the sense that it does follow certain pattern. However, it's only on a broader level. However, if you kind of, really go and try to mimic every individual structure, it's near impossible to match it, like even qualitatively, with experiment, let's say, on a small scale as well as large scale. And so what they're trying to do is use this quantum inspired or quantum phenomena to recreate that. And so that's what that's one aspect of how quantum can be used, and this is one of the examples of it. The other example is a whole field of quantum inspired algorithms, where quantum inspired, again, this is a very similar phenomena where you're using quantum principles to then speed up your regular computing. Again, this is computing is done on traditional, so your regular CPUs, GPUs, HPCs. You're still using your traditional computing. However, the way you're actually performing your calculations or your methodology changes to be more fitted and has more principles of quantum integrated into it. And of course, this is not a very wide net approach. And as we will see in quantum, it's not a wide net approach where quantum can be utilized for everything. Like if, let's say, this operating system that we're using, there's no need for quantum, to be honest. It's quite fast as it is. We don't necessarily need an extra power for quantum to do that. However, there are cases where quantum is needed. And one of these cases right now that we can readily use is this quantum inspired. And this problem of optimization is quite readily, is a very interesting problem where there are many different approaches in quantum inspired optimization, where you have your quantum annealing or quantum inspired annealing, sorry, which is similar to simulated annealing, but this quantum inspired annealing is utilizing the whole aspect of quantum tunneling and using that to advantage to go to adjacent states, where go across the adjacent states. So simulated annealing is essentially, if you go down a valley, you can only go up until certain points to get out of this valley, let's say. But quantum tunneling, you can go from one valley to another valley, or that's much far in distance as well. There is no restrictions in doing that. And so this is quantum inspired annealing. And what we're really doing for this type of algorithm is to mimic what an actual quantum annealing would do, because quantum annealing devices, they will kind of go from one hill to another hill quite readily like that. There is no restriction for that because they use quantum tunneling, the whole principle of quantum tunneling, and it's embedded into their quantum systems. And so the different types of optimization problems that we have from the industry, this is one of the most widely applied area right now, the hot areas of industry for quantum. And so in the automotive area, there is a whole aspect of traffic flow simulation. In the aerospace, you have the whole, again, the traffic flow management. You have the route optimization aspect of it. On the airline front, you have the revenue management, not just airline, but in any front, you have the revenue management program. And from financial, we have market simulation of performing Monte Carlo based simulations, or portfolio optimization, where you have a bunch of companies in your portfolios and you want to invest in, and you want to essentially create a risk benefit analysis to do that. And currently, financial institutions, they currently do that. However, the fidelity or the accuracy of it is quite low. So quantum has a can provide tremendous impact in this. And we're one aspect of BosonQ side. We're kind of beginning to look at this whole financial sector as well. Then now just talking in the whole sense of just simulations, we have various different aspects of it, from biological to chemical, thermal simulation, as well as structural simulation. So, biological or chemical, there is drug target interaction, chemistry-based simulation. You have the molecular simulation, as well as drug discovery. That's a very big topic for quantum. In thermal simulations, we have the whole term battery manufacturing and how thermal really plays a role in that. And we actually just published an article of battery thermal management system, and we've seen lots and lots of incidents, especially in India, happening due to various different reasons, but a lot of incidents where the EVs are catching fires while charging, while they're actually being operated, whatever may be, and some of them are actually lethal. So this is a very big issue right now, at least in India, as well as throughout the world, where more and more EVs are emerging. However, the right technology isn't nearly there, especially in the thermal aspect of it. And and of course, the battery capacity is always going to be a big issue. The how long your range is. And so that's whole aspect is thermal simulation. And lastly, the structural simulation, where you want to perform crash types of simulation, where a car kind of crashes into a wall. And if to try to do this simulation, computer simulation, currently it takes about a day for a single simulation run. And people have done, and this is on HPC, of course, and people have tried using commercial software. Companies have tried using commercial softwares. However, they're getting okay to good results, but they, again, don't necessarily have the freedom to spend more time on it, because of course, the longer your simulation runs, one, you can use a much more accurate model, but that has it's kind of like a seesaw. If you want more accuracy, you're gonna have to spend more time. So it's kind of like that. And so now looking at the long-term applications of it, now this is where things get really interesting, because when we're still talking in terms of long-term, we're looking at where quantum can really play an advantage and go for things that aren't necessarily being able to solve at the moment. And so the future towards bigger NISQ devices and fault-tolerant quantum devices, which that implies that we will have a much higher qubit count, as well as the fidelity of each individual qubit will increase as well. On top of that, there will be a decrease in the error rate. And when we go to the whole aspect of fault-tolerant quantum computers, there'll be at negligible levels, where we don't necessarily even need to have any post-processing on essentially error correction codes, which we currently do. And they'll be at the same fidelity or accuracy as our computers are, 10 to the minus 16 type of computer zero type of accuracy. And so with that, we can perform more complex simulation. And so where this is really interesting is that it enables really complex fluid simulations, where this whole aspect of, in fluid mechanics specifically, the governing equation which we follow and which dictates how a fluid itself will kind of behave. It's actually a millennial problem. It's $1 million problem, because there is no closed-end solution. Hence, we need a numerical analysis to be performed. But with this quantum-based devices, full-on fault-tolerant quantum-based devices, what that will enable us is that even though we don't have a full-on closed solution, an analytical solution for every single type of problem, we can use computer to get accurate solution. When I say accurate, you can kind of replace it with experiments, and qualitatively as well as quantitatively, we cannot tell the difference between the two. And this has been one of the biggest things in this whole CFD or fluid mechanics field, as well as in many different fields. We have that, the top end modeling that we do, where in academia or in few sample cases, we can perform it. However, it's not very widely applicable. And that's why we see a lot of areas of AI, ML type of technologies really penetrating the simulation field as well, because they also want to try to recreate that or replicate that using that whole aspect is, image processing is one aspect of the PINN, or physics informed neural networks, or those types of ML based techniques are another methods to try to recreate that, like, creme de la creme kind of simulation accuracy. But we really believe quantum can really provide that. The second is the coupled system simulations, where, again, now we're not even talking about a very complex single physics system or simulation, but we're now talking about, okay, now suppose we're doing a crash analysis. Now, once your car crashes into a wall, how is your fuel tank, or how is your fuel tank going to react to that? Will any of the components in your car puncture your fuel tanks? If it punctures it, how will the fuel leak out of it? Is it going to be very slow trickle? Is it going to essentially start going off like a sprinkler? And if so, if there is enough heat there, can it actually ignite? And so now we're just adding more and more complexity to it. And so this whole aspect of it is currently we don't do it. In essence, we just don't do these types of simulations. These are sure maybe very specialized cases, but we want to be able to get to that cases where we don't have any computing restriction. If our minds can imagine it, we should be able to recreate it using simulations. That's the whole aspect that we come from at BosonQ side, but also there's a lot of benefit to that from the industry point of view as well. The third one being MDO, or multidisciplinary design optimization. Again, here you're using multiple different physics in your and trying to recreate it. But now you're trying to change your entire design from that. A great example of this would be aircrafts have been around for about 70 years. Well, commercial aircrafts have been around for like about 70 years. I think 1950s, 60s is when it started. So about 70, 80 years. However, the design, the outside exterior design has relatively changed the same. And of course, it follows very well with the actual physics of it. However, there hasn't been a breakthrough in aerospace, especially in aircraft designs, since past 80 or so odd years. From there, if you look at any other technologies, things have progressed so much. In the automotive, if you look at, let's say, the motorsports aspect, there is a tremendous development on the engine, on its efficiency, as well as how fast and how much better the performance is. And that ultimately gets trickled down into your commercial-based sectors as well. In electronics, I mean, of course, computers were invented even after airplanes were there. And yeah, we all know how electronics as a whole has grown exponentially since then. But coming down to it, airplanes have remained essentially the same design. And as an aerospace engineer, it kind of breaks my heart. So this is where we really want our software to come and play a big role, is help industries adapt quantum so that they can perform new types of simulations and make much better designs than what we already have. And the last one, chemical reaction database, creating a database for chemical reactions. And of course, there is already a database for chemical reactions. However, more and more different chemicals are being discovered, especially on the material design as well as the pharmaceutics aspect of it. And with that, not only we want to create more more materials, but also have a whole database where we can kind of make sure that the stability, now talking about pharmaceutics aspect, the stability of a compound or a drug from top to bottom, we have all the information, the degradation rates of it, the reaction kinetics with other compounds or other drugs, whatever may be. This is, we really think this fault tolerant based quantum computers can really provide a big change in that. And now, and so these are the short and the long-term applications that I talked about. Now I really want to talk about what we're doing at BosonQ and how we are trying to enable those, at least right now in the short term, near term, how we can utilize those techniques to bring solutions and, in our case, a software which the industries can readily utilize and get some essence of quantum advantage. So of course, there's going to be a small small advantage from traditional computing, since we are going to be using quantum inspired or this NISQ era quantum computers. So it's not necessarily going to be the 1,000 or exponential, whatever the speed of that everybody talks about. We might not necessarily see it right now. However, there is a potential for increase in performance right now with these two techniques that we have. So at BosonQ, we're developing this BQ5 software. And so this BQ5 meaning physics. And so this software suite we're developing is an engineering simulation software suite where what we're really going for first is our design optimization. That's because, as I mentioned, in optimization, that's one of the best applications from industries where we can readily apply it, as well as it has shown tremendous potential to show some form of quantum advantage. Then the second level aspect, we have our thermal analysis and our structural mechanics. These are two other physics that we have developed. We just started developing this fluid dynamics, or the CFD, as I've been saying. We started developing that, and we are actually working with a client at the moment in developing this near-term quantum advantage, showing near-term quantum advantage even for CFD. And what we eventually want to get to is different other aspects of it, of electrochemistry, electromagnetics, acoustics, and the ultimate goal is the combination of few of them and as well as all of them, which is the whole multi-physics simulation that we speak of. So I'm going to be now showing a few examples of what our software BQ5 already in action. And so this is our design optimization module that we've created. So this is kind of talking about the whole methodology of how we even came with the whole design optimization module. Is we started off with this quantum inspired based approach of optimization, where we wanted to see how quantum can really play a role, or quantum principles can really play a role compared to your traditional computing. And so we set off on this one venture of, okay, exploratory phase, let's just see, and let's try to create this optimization, an optimization technique or an algorithm. And so first we benchmark against several different cases, and so if it proved to be as good as your traditional computing in terms of finding the accurate answer, or in this case, the optimized solution, and in lesser time, or it actually beat it. So not only we were able to just showcase that we can match it, but also in some instances we were actually beat it. Thus, it's kind of showing that there's a whole potential where looking at problems where we can beat it. And then we kind of went towards this, the middle one is our airfoil optimization, where we started off with a very optimized airfoil, which is a wing shape. Essentially, this is how like an airplane wing is essentially designed, this 2D cross section of it. And so using an already optimized wing shape, we tested our optimization algorithm. And if I can zoom in, Yeah. And so this blue is our initial shape, and the orange is the optimized shape. And so we decrease the overall thickness of it in essence, but just by doing that, we actually showcased improvement in the whole performance of this wing shape by 5%. And even though 5% doesn't seem that high, we started off with an already optimized wing shape. So each and every single of these airfoils are created based on their specific use cases, and then they're optimized for it. So we use that optimized one, and then use the same exact criteria, and then try to optimize it even beyond that point, and we were able to do that. So again, this is shown, over and over. I'm kind of saying the same thing, where this is really showing that we can actually find a much better solution and a more optimized solution than what we can get from traditional computing. And the biggest advantage of it is, or how it is possible, is I can actually show you in this functional analysis that we did, is that here our goal was to find the deepest valley in this. I think this is the holder function, if I'm not mistaken, but there are many different values. And many of the optimization algorithms actually have the tendencies to get stuck in the intermediate valleys. And if the intermediate valleys are deep enough, it's really difficult for the solution to, once it's down a rabbit hole, it cannot climb itself out of it. But here we can use since we're using quantum inspired approaches, we're essentially not restricted to that approach. And we can use techniques of quantum tunneling, superposition, things along those lines to perform or check many different valleys, and then see, okay, which valley is the best one. And so in this case, all four of these valleys were the most optimized solution, or the minimal point. And our solution was actually able to find all four of them. And it's not necessarily finding a one solution. We found four different solutions. In this case, there are only four solutions as well. So we found all four of them with our algorithm. And so now, from the 2D case, we went on to now a even more complicated case of trying to optimize this. This is called a control arm, which is used for your steering column in an automotive space. It's used to link your steering column to your transmission. So this is a very integral part, and traditionally this whole portion is a solid triangular piece. However, there is no need to have a solid triangular piece, because even though it's made of aluminum, you're wasting a lot of material. There's added weight to the whole vehicle as well. And so we sought out to find a more optimized solution. And this is essentially the final shape that we got, where if you essentially cut out this portion of it, remove the guts of this triangular piece, we can get a much better optimized solution. And of course, this is me trying to qualitatively explain it, but that's not the whole approach. The approach is very systematical. But yeah, this was actually done from our POC with one of our clients. And yeah, so this is the final solution that we got. And since it's optimization, there are constraints and objective function that we have to set by, and we were able to minimize or get the objective function of reducing the mass. Now, moving on to the next module, or the next phase that we are going to be launching is the structure module. So in the structure module here, you see this is again an automotive example. This is a very crude automotive example where you have essentially the bones of the car, the skeleton of a car. And so here is essentially your front bumper, and this is replicating what it might be like if you kind of ran into a brick wall or something. So you have a distributed load along the front of the vehicle, and on the right side, this is the displacement, or how much the shape of this car will change. And so here, and this is essentially the displacement that your whole car will change. Now, the interesting thing about this is that this was actually performed on an actual quantum computer. And so we, so how we actually perform it on quantum computers, I know I've said that, yeah, right now quantum computers aren't that great because, they're very error prone and such. However, there are techniques to reduce the errors, and we've developed and utilized these techniques to get the errors down low, to be so that they are ready for industry level cases or industry level answers or solutions that we can provide to them. And so this is a small demonstration case that we did. And if I remember correctly, this was done on Deega's annealing system. But yeah, so again, this is on a quantum system. The next module, this thermal module, again, this is, we took an automotive example again, where this is a radiator in a car. So in this case, our regular automotive radiators are 3D, but since it's the same shape, kind of extruded into the third dimension, we can very well just do the simulation as if it's a 2D based simulation. And so these are all the boundary conditions where you have your fixed temperature in the center column, and then you have your heat kind of radiating outward, and your convective cooling, your cooling since your car is going to be moving. So that's going to be cooling your this whole radiator. And on the right side is the answer that we see. The heat essentially diffusing from 150 degrees from the center column Celsius all the way down to the near 50 degrees towards the end of the radiator. Again, this was done on Deviate's quantum machine. So again, we're showing this NISQ era capabilities on quantum computers on industrial use cases. And so, yeah, now the next case that we've done, and we actually published an article on this, is it's a heat exchanger. So again, the whole aspect of heat exchanger is to decrease the heat or take the heat out of the center, the rod that you see on the left hand side. That's where hot gas is kind of going through, and you want to decrease the heating of the pipe itself. And so you put this type of exchanger in the middle, and that exchanger is, if you think of let's say it's made of copper, then it can kind of take the heat out of the main, let's say, aluminum tube. And so on the right hand side is the solution that we get, and this actually was done on quantum simulator. And so with all of this, we can showcase readily that we have the capability of doing it on quantum inspired approaches, quantum simulators, as well as on a NISQ based devices. And so in essence, all of our development from the very beginning, from the essentially the inception of our company, we kind of made this claim that, not claim, but we kind of set this direction of BQP or BosonQ Psi to be that we don't necessarily want to restrict ourselves on using a single type of architecture, quantum-based architecture. And so from that, yes, it made our jobs very, very difficult. However, it's actually reaping rewards right now, where we're not restricted to use, let's say, quantum annealing or just gate-based. We can interchange which one we use. And we've developed several different approaches that enables us to do that. And so in any of these physics or BQ Phi in our software, we will give the user the ability to choose whether or not they want to do it in simulator on a quantum annealing or on gate-based architecture. And even on gate-based, we're not restricted to, let's say, IBM's superconducting or IonQ's ion trap-based quantum system, or photonics. We're not restricted to any of that. We can use any different architecture as well as any computing services that we have access to. And so this is one of the biggest USPs or unique selling points that we have for our customers, is that there's no restrictions on quantum computers right now from our end. And so this is BQ Phi. Now, another use case that actually we performed at BosonQ Psi, and actually this is for route optimization for different airlines. And actually, I was invited down to Geneva at IATA's conference where they were doing a technology spotlight on quantum. And we've actually published this results of trying to do route optimization of airlines and different aircrafts that are going with several different destinations. I think in here we were simulating about 100 flights, yeah, all across Europe with several different origins and destinations. And the whole essence of it was to reduce the carbon emissions, the carbon footprint that the aircrafts kind of lay on, kind of produce. And so this is one of the biggest issues that we've always had. Once the whole carbon emission became a really important, is aircrafts produce way too much carbon footprint to the whole, to any industries. And so with this, we can actually utilize, we started off with different set of origins, set of destinations, and then trying to find which is the best flights, or which from which origin to which destination, and when during the time of the day they need to go to reduce the overall carbon footprint. And from this, we actually reduced the carbon dioxide by 220 tons. And again, this is in 100 flights in a single day. So imagine what the implications of this throughout the whole year. And now we're talking about trans-Pacific or transatlantic kind of flights. The carbon footprint would be diminished by a tremendous amount. And on top of that, from the airline point of view, the fuel prices have been higher than ever, and in the US we've kind of seen a lot of it as well. Especially you guys in California, the fuel rates are ridiculous over there. So from the airline point of view as well, they actually see cost advantage of essentially performing these types of simulations where they can get fuel consumption to be decreased. And here we estimated the cost of fuel to be decreased by $70,000. And again, this was done maybe a month back. So yeah, about a month back. So maybe this might have increased based on our fuel prices. But yeah, so this is actually one of the results that we showcased for that. And we got a lot of traction and notice from the whole of airline industry. Now, I just want to quickly showcase some of the things that we've done at BosonQ side. So we've got accepted into Microsoft for Startups, as well as we are an APN or Amazon partner network. We're in their partner network section as well. So it's definitely great to see two different services where we can utilize their quantum services as well, because we also have quantum, we're in their quantum programs as well, each of them respective. Additionally, we have some contracts signed with TCS and actually being inducted into their Coin Accelerator program. So TCS being Tata Consultancy Services, which is one of the largest system integrators in the world. And so, yeah, it's a really beneficial to BQP to be partnered with such a big organization, which has thousands of customers throughout the world. Then we also actually just graduated from the prestigious QTech program from University of Bristol, QTech's Quest program from University of Bristol. Like I mentioned, I was invited to IATA, hosted by Plug and Play. We're making big improvements, as well as being key leaders in India in the National Quantum Technology Commission that is there. Since it's a startup, we actually do have we won a Matrix Innovative Startup award just this past month, and we got invited in. We won few challenges here and there from the inception as well. And so just to summarize, I can just leave this up here as well. And if anybody has any questions, I would love to go into that. But in essence, out of this whole talk, I really wanted to showcase the near and the long-term applications of quantum computing are, what are the restrictions and what are the possibilities that long-term quantum computing, or how fault-tolerant quantum computing can enable us with the vast amount of applications that we still have to deal with, and additionally how BQFI can really come in and play that role as a simulation company.